Right now, the fastest object humanity has ever built is hurtling through space at a speed of 430,000 miles per hour. At this almost unimaginable velocity, you could circle the Earth in less than 4 minutes. And yet, even a spacecraft moving this fast enough that any collision would instantly destroy you, would still need more than 6,000 years to reach the nearest star. This is where our intuition about space travel begins to break down. The distance a human could travel in a single lifetime is not truly limited by engineering, by money, or even by determination. It is constrained by something far deeper, a boundary woven into the very structure of reality itself. And yet, within that boundary, there exists a subtle possibility, one that could allow a person to cross millions of light years while experiencing only a few decades of time. The fastest object ever created by human hands is currently racing through space at a velocity that defies everyday experience. The Parker Solar Probe, launched in 2018, has reached speeds exceeding 430,000 miles per hour during its closest approaches to the Sun. At this velocity, the probe can cross the entire continental United States in less than 25 seconds. It moves so fast that if you were standing in New York, you could blink twice and it would already have passed Los Angeles, continued across the Pacific Ocean, and be nearing Hawaii. This achievement represents the absolute peak of human engineering. After decades of technological progress, billions of dollars invested, and the combined effort of thousands of scientists and engineers, the Parker Solar Probe uses a sequence of gravitational assists from Venus to accelerate to speeds that no chemical rocket could ever reach on its own. With each flyby, it takes a tiny fraction of the planet's orbital energy, slowly increasing its velocity through years of carefully planned trajectory adjustments. The probe stands as humanity's greatest attempt to move rapidly through the vast emptiness of space. To truly understand how remarkable this speed is, it helps to look back at the entire history of how fast humans have ever traveled. For most of our existence as a species, the fastest a human could move was about 25 miles per hour, the speed of a running horse. This limit remained unchanged for more than 200,000 years. By the year 1900, automobiles had surpassed 60 miles per hour. In 1903, the Wright brothers flew at 34 miles per hour, and within 60 years, test pilots broke the sound barrier at 761 miles per hour. By 1969, Apollo astronauts returning from the moon reached nearly 25,000 miles per hour. The fastest speed any human has ever experienced. The Parker Solar Probe travels 17,000 times faster than those Apollo astronauts. It moves at such an extreme velocity that no human could survive on board. Not because of the speed itself, but because its path brings it close enough to the Sun to encounter temperatures exceeding 2,500 degrees Fahrenheit. This is speed achieved through decades of gravitational precision, not brute engine power. And yet, even this extraordinary velocity reveals a difficult truth about our limits in space. At 430,000 miles per hour, the Parker Solar Probe would still need around 6,600 years to reach Proxima Centauri, our nearest neighboring star, located just over 4.24 light-years away. To put this into human terms, a journey that began when the ancient Sumerians first invented writing would only now be nearing its destination. A human lifetime lasts around 80 years. That means, even at the fastest speed humanity can currently achieve, you would travel just over 1% of the distance to the nearest star before your life comes to an end. The numbers become even more unsettling when you look at what a single lifetime actually achieves at these record speeds. If you traveled continuously at the Parker Solar Probe's maximum velocity for 80 years, you would cover about 3 trillion miles. Written out in full, that number contains 12 zeros. It sounds enormous. almost beyond comprehension, until you compare it to the true scale of space. 3 trillion miles is only about 0.05 light-years. The nearest star system is more than 80 times farther than what an entire human lifetime at that speed could reach. You could spend your whole life traveling and still never come close to leaving our stellar neighborhood. The Oort cloud offers another perspective. This vast, frozen sphere of ancient comets marks the outer boundary of the Sun's gravitational influence. It stretches as far as 100,000 astronomical units from the Sun, where 1 astronomical unit is the distance between the Earth and the Sun, about 93 million miles. This region represents the true edge of our solar system, the point where the Sun's gravity finally fades and interstellar space begins. At humanity's current top speed, reaching even the inner edge of the Oort cloud would take roughly 600 years of continuous travel. A full human lifetime, even at unprecedented velocity, would not be enough to escape the Sun's extended gravitational domain. We would pass away long before ever leaving this distant cloud of orbiting debris. In fact, an entire lifetime of travel would amount to less than crossing from Manhattan to Brooklyn when compared to the scale of our cosmic surroundings. To understand this more clearly, consider the journey of the Voyager 1 spacecraft. This remarkable probe has traveled farther from Earth than any human-made object in history. After more than 47 years moving through interplanetary and now interstellar space, Voyager 1 has covered roughly 15 billion miles. It has taken nearly half a century to reach this distance. And even now, it continues to move farther away with every passing second. Voyager 1 crossed the heliopause in 2012, officially entering interstellar space. This boundary marks the point where the Sun's solar wind can no longer push back against the pressure of the interstellar medium. The thin gas and dust that fill the space between stars. Many headlines claimed that Voyager had left the solar system. That is true in one sense, but also misleading in another. The probe has escaped the Sun's magnetic influence, yet it still remains within the Sun's gravitational reach. It will not pass beyond the Oort cloud for another 30,000 years. 15 billion miles may sound immense, but it represents less than 0.003% of the distance to the nearest star. If the journey to Proxima Centauri were scaled down to a road trip across the United States, from New York to Los Angeles, roughly 2,800 miles, Voyager 1 would have traveled only about 100 feet in 47 years. You would still be standing in your driveway, barely beyond the mailbox after half a century of continuous driving. Your neighbors would watch you grow from youth to old age. While your car remained visible from their kitchen window, there is another way to understand this gap. Light travels at 186,000 miles per second. In the time it takes to read a single sentence, light can circle the Earth several times. Voyager 1, after nearly 5 decades of travel, has covered a distance that light would cross in about 20 hours. Its 47-year journey is equal to less than a single day of light travel. The 4-year journey that light needs to reach Proxima Centauri is more than 150,000 times farther than Voyager has traveled in nearly half a century. Voyager 1 moves at about 38,000 miles per hour relative to the Sun. Impressive by human standards, but it reveals the enormous gap between what we can achieve and what the universe requires. At this speed, the probe would need more than 70,000 years to reach Proxima Centauri. By the time it arrived, if it could survive that long, the humans who launched it would have been gone far longer than our entire species has existed. Homo sapiens appeared roughly 300,000 years ago. Voyager would need to travel for nearly a quarter of that time just to reach our nearest stellar neighbor. And, in reality, the probe will not survive the journey. Voyager 1 is powered by a plutonium source that produces electricity through radioactive decay. Each year, this power decreases by about 4 watts as the fuel slowly runs out. By the year 2025, it will no longer have enough energy to operate its scientific instrument. By 2036, it will fall completely silent. continuing onward as a lifeless object drifting through space. For tens of thousands of years, it will travel alone, a quiet trace of human ambition, moving through the darkness with no destination, and no possibility of ever being seen again. The fundamental problem lies in the underlying physics of chemical rockets. Every rocket humanity has ever launched operates on the same basic principle that once sent the first Chinese fireworks into the sky more than 1,000 years ago. Hot gas is expelled from one end, pushing the vehicle in the opposite direction. It is Newton's third law in its most elegant form. You push mass backward, and the reaction force carries you forward. Simple, effective, and yet deeply limited when it comes to traveling between stars. Chemical rockets face a hard boundary described by the Tsiolkovsky rocket equation, a relationship developed by Russian scientist Konstantin Tsiolkovsky in the year 1903, which defines the maximum speed a rocket can ever reach. This limit depends on two key factors. The first is the exhaust velocity of the propellant, essentially how fast the rocket can throw material out the back. The second is the ratio between the rocket's initial mass, including all its fuel, and its final mass after that fuel has been burned. For chemical propellants, exhaust speeds reach only about 4.5 kilometers per second. This is not a problem waiting for a clever engineering breakthrough. It is a fundamental limit set by the chemistry of combustion itself. Even with hydrogen and oxygen, the most energetic chemical reaction we can realistically use, the resulting steam molecules can only move so fast. The energy released when chemical bonds break and form has a strict upper limit. No amount of ingenuity can force those molecules to leave a rocket nozzle faster than the laws of chemistry allow. And this is where the true constraint becomes clear. When you calculate what would be required to reach even a small fraction of the speed of light with chemical rockets, the results become almost impossible to accept. To accelerate a small probe of just 1,000 kilograms to 1% of light speed, you would need a starting fuel mass greater than the total mass of the observable universe. Not just the Earth, not just the Sun, not even all the stars in our galaxy combined, but everything that exists. This is not exaggeration. It is what the mathematics actually tells us. The rocket equation includes an exponential relationship that severely punishes any attempt to reach higher speeds. Each increase in velocity demands not just more fuel, but exponentially more. The curve rises so steeply that it quickly surpasses any physically meaningful amount of matter. Gravity assists offer a partial way around this limitation, allowing spacecraft to gain energy from planets without using additional fuel. By carefully timing close flybys of massive bodies, a spacecraft can exchange momentum with planet, gradually building up speed through gravitational interactions. The Voyager probes made extensive use of this technique, moving from Jupiter to Saturn to gain the velocity needed to head toward interstellar space. The Parker Solar Probe uses repeated flybys of Venus to accelerate to its record-breaking speeds near the Sun. The process works by falling toward a planet and gaining speed as gravity pulls you in, then leaving along a path that transfers some of the planet's orbital momentum to the spacecraft. The planet loses an almost immeasurable amount of energy, while the spacecraft gains a significant increase in speed. Jupiter, for example, moves ever so slightly slower after each Voyager flyby, though the effect is far too small to detect directly. Even so, gravity assists come with strict limit. The solar system contains only a limited number of large bodies positioned in ways that can provide useful acceleration. Jupiter is the most powerful source of gravitational assistance we have. But each encounter can only transfer a finite amount of energy. Every boost also requires time, sometimes years, to travel to the next planetary alignment. The same orbital mechanics that make these maneuvers possible also restrict how much total energy can be extracted. A spacecraft designed to maximize these flybys, moving between planets over decades of carefully planned trajectories, might eventually reach speeds close to 150,000 miles per hour. This is about 4 times faster than Voyager's current speed, achieved only through long periods of precise navigation. And yet, even that is far from enough. At such speeds, reaching even the nearest stars would still take tens of thousands of years, far beyond any human lifetime. The fastest outward journey achieved mainly through gravity assists belongs to the New Horizons mission, which passed Pluto in 2015 at a speed of about 36,000 miles per hour relative to the Sun. After receiving a major boost from Jupiter in 2007, the probe raced outward through the solar system, faster than any spacecraft before it. The images it sent back of Pluto revealed a world far more complex and striking than anyone had expected, with vast nitrogen plain, glacier, and mountains made of water, ice. And yet, even at this remarkable speed, it would still take more than 80,000 years to reach the nearest star. Ion engine technology offers a modest improvement over chemical rockets by greatly increasing exhaust velocity. These engines work by ionizing a propellant, usually xenon gas, then accelerating the charged particles using electric fields. The ions leave the engine at speeds 10 to 20 times higher than chemical exhaust, making the system far more efficient at turning propellant into motion. The Dawn spacecraft used ion drive systems to explore the asteroid belt, becoming the first mission to orbit 2 different celestial bodies beyond Earth. Its engines allowed it to adjust its trajectory gradually over months of continuous thrust, performing maneuvers that would have been impossible for chemical rockets with similar mass. But ion engines produce extremely small amounts of thrust, and this limits their usefulness for rapid acceleration. Dawn's engine generated only about 90 millinewtons of force. To picture this, imagine placing a single sheet of paper on your hand. The weight pressing down is roughly equal to the thrust of an ion engine. This tiny force, applied continuously over years, can build up meaningful speed, but doing so requires patience measured in decades, not the short bursts used by chemical rockets. Even with unlimited fuel and a full century of operation, ion drive technology cannot reach the speeds needed for interstellar travel within a human lifetime. You could run an ion engine for your entire life and still fall far short of the velocities required to significantly shorten the journey to nearby stars. The technology is incredibly effective for precise movement within the solar system, but it does not solve the deeper problem of interstellar distance. Ion drives are impressive in what they achieve, but what they achieve is not enough. The next step in motion is the nuclear thermal rocket. These engines pass hydrogen propellant through a nuclear reactor, heating it to extremely high temperatures before expelling it through a nozzle. This process allows the hydrogen to reach speeds about twice as high as those produced by chemical combustion, effectively doubling exhaust velocity and easing some of the limits imposed by the rocket equation. NASA studied this technology extensively during the NERVA program in the 1960s and early 1970s. Engineers conducted many successful tests, running nuclear engines for long durations and showing that the concept works reliably. The technology was nearly ready for use before political and budget decisions brought the program to an end in 1973. We have known how to build nuclear rockets for more than 50 years, but chose not to pursue them further. In theory, a nuclear thermal rocket could accelerate a spacecraft to around 100,000 miles per hour with practical fuel ratios. This is a major improvement over chemical rocket, roughly tripling the speeds we can currently achieve through combustion alone. The journey time to Proxima Centauri at this speed would fall to around 28,000 years, still far beyond a human lifetime, still longer than all of recorded human history. But it is, in some sense, progress. Solar sails offer perhaps the most elegant idea for propulsion. using the pressure of sunlight itself to move a spacecraft without carrying any fuel. When photons strike a reflective surface, they transfer a tiny amount of momentum, gently pushing it in the direction the light is traveling. If the sail is large enough and light enough, this pressure can slowly build speed over time. The Japanese Icarus spacecraft demonstrated this concept in 2010, successfully deploying a 14-meter sail and showing that sunlight alone can produce measurable acceleration. It confirmed that light can indeed move objects through space, and that advanced sails could one day travel without carrying any propellant at all. Near the sun, where radiation is strongest, a solar sail could in theory accelerate at close to 1% of Earth's gravity. That may sound significant, but it comes with a limitation. To maintain that acceleration, the spacecraft must remain close to the sun, while the purpose of propulsion is to move away from it. As the sail drifts outward, the intensity of sunlight drops rapidly. If you double the distance from the sun, the radiation pressure falls to just 1/4. What seems effective near the sun quickly becomes negligible in the outer solar system and disappears entirely in interstellar space. A solar sail launched from a close solar pass might reach speeds of several 100,000 miles per hour before the push from sunlight fades. At around 500,000 miles per hour, roughly 100 times faster than Voyager, and beyond any speed we have achieved so far. The journey to the nearest star would still take more than 5,000 years. In a full human lifetime, you would travel about 350 billion miles, or roughly 0.6 light years. That is only about 1/17 of the distance to Proxima Centauri. It is meaningful progress, but still not enough. You would spend your entire life traveling through the darkness between stars without ever arriving. This is the difficult reality of current and near-future propulsion. The fastest speeds we can build, or realistically imagine in the coming century, are not sufficient to carry a human beyond our immediate cosmic neighborhood within a single lifetime. Chemical rockets cannot reach the required speeds. Ion engines are too weak. Nuclear thermal rockets improve the situation, but only slightly. Solar sails cannot accelerate large spacecraft fast enough. For now, we remain confined, limited to a region just a few light hours from our home world. The psychological weight of this limitation shaped how early scientists viewed interstellar travel. Many physicists in the 20th century believed that traveling between stars was simply impossible for living beings. The energy required seemed overwhelming. The journey times stretched far beyond anything we could consider practical, and the radiation exposure during voyages lasting decades would likely be fatal. The vast emptiness between stars began to feel almost intentional, as if the universe itself were preventing life from moving between star systems. Some scientists even suggested a kind of cosmic isolation, where intelligent species remain confined to their homeworlds, separated by distance alone. The speed of light appeared to be an absolute barrier, one that no level of engineering could overcome. We might one day communicate with distant civilizations using signals that take years or centuries to arrive, but visiting them, standing on another world, or meeting another form of life seemed forever out of reach. In this view, the universe did not forbid exploration directly, but through the strict mathematics of space and time, it made such journeys effectively impossible. And yet, within those same equations, there is something unexpected, a possibility that changes how we understand distance, time, and the limits of exploration. This possibility was uncovered in the year 1905 by a 26-year-old patent clerk working in Bern, Switzerland. His name was Albert Einstein. He asked a deceptively simple question: what would it be like to travel alongside a beam of light? What would you see? How would time behave? And what would happen to the space around you? The answers he discovered challenged everything intuition had suggested about motion, time, and distance. They revealed that the barrier confining humanity to its local region of space is not as rigid as it appears. Distance and time are not fixed in the way everyday experience leads us to believe. They can change. They can stretch and compress depending on how fast you move. A clock on a fast-moving spacecraft does not tick at the same rate as one on Earth. A measuring rod carried by a traveler does not keep the same length as an identical rod at rest. The universe behaves in ways that feel almost counterintuitive, allowing what once seemed impossible to become, at least in principle, achievable. To understand how far a human could truly travel within a single lifetime, we have to let go of our usual intuition about motion. We must step into a framework where time itself flows differently depending on speed, where distances contract for those in motion, and where the 80-year limit of a human life becomes far more flexible than it first appears. The universe seems to operate under rules that almost appear designed to limit our ambitions of exploring the stars, and yet, within those same rules, there are hidden possibilities that could allow a single human lifetime to stretch across distances we currently observe only through telescope. The very physics that creates the barrier of light speed also provides a way to make that barrier almost irrelevant, at least from the traveler's perspective. What comes next begins to reshape how we think about speed, time, and the true limits of exploration. The cosmic boundary we appear confined within is not completely sealed. There is a way through, and the key lies within the laws of physics themselves. In the year 1905, a 26-year-old patent clerk in Bern, Switzerland submitted a paper to a German physics journal called Annalen der Physik. The paper had a modest title, offering no hint of how deeply it would change our understanding of the universe. It was written without advanced mathematics, with very few references, and by someone with no formal academic position or laboratory, yet this single work would overturn centuries of assumptions and reveal that time itself is not fixed, but can change depending on motion. Albert Einstein began with a simple idea: the speed of light in a vacuum is always the same. No matter how fast the observer is moving, whether you are standing still on Earth or traveling through space at half the speed of light, you will measure light moving at exactly 186,000 miles per second. This is not a limitation of measurement or technology. It is a fundamental property of reality. And from this single idea, Einstein uncovered consequences that challenge our deepest intuitions. If the speed of light must remain constant, then something else has to adjust. That something is time. Clocks on moving spacecraft tick more slowly than identical clocks at rest. This effect, known as time dilation, seemed almost impossible when it was first proposed. How could time itself, something so basic and universal, change depending on motion? Yet the mathematics left no room for doubt. And over time, experiments confirmed the prediction: time dilation is real. It can be measured, and it reshapes what is possible for human travel. The relationship between speed and time follows a precise rule. Einstein introduced a quantity known as gamma, which tells us exactly how much time slows down at a given velocity. It is calculated by taking 1 divided by the square root of 1 minus the square of your velocity divided by the square of the speed of light. At everyday speeds, this effect is almost invisible. A car traveling on a highway experiences time dilation so small that even the most accurate clocks can barely detect it. A passenger on an airplane ages only a few nanoseconds less than someone who remains on the ground during the same journey. The effect is real, but at everyday speeds it has no meaningful impact on our lives. Everything begins to change only when velocity approaches a significant fraction of the speed of light. At 50% of light speed, the gamma factor reaches about 1.15. Time on board, the spacecraft passes around 15% slower than on Earth. 1 year experienced by the traveler corresponds to roughly 14 months on Earth. This difference is noticeable, but still limited, at 90% of light speed. Gamma rises to about 2.3 for every year that passes on the spacecraft. More than 2 years pass on Earth. A journey lasting 50 years for the traveler would mean over 100 years unfolding back home. They would return to find generations aged beyond recognition, grandchildren grown old, and great-grandchildren shaping a new world. At 99% of light speed, Gamma reaches about 7.1. Now the effect becomes far more dramatic. 7 years pass on Earth for every 1 year experienced by the traveler. 10 years on the ship would equal 70 years on Earth. A journey lasting 50 years for the traveler would span more than 350 years of Earth's history. You would leave behind one civilization and return to something entirely different. At 99.9% of light speed, Gamma exceeds 22. 22 years on Earth are compressed into a single year on board. A 50-year journey for the traveler would correspond to around 1,100 years on Earth. Entire eras of history would pass during a single lifetime. As velocity moves even closer to the speed of light, the pattern continues. At 99.99%, Gamma exceeds 70. At 99.999%, it rises above 223. At 99.9999%, it passes 700. Each additional digit brings a dramatic increase, roughly multiplying the effect by 3 each time. These numbers completely change how we think about interstellar travel. Consider not just the nearest star, but something farther away. Vega, one of the brightest stars visible in our night sky, lies about 25 light-years from Earth. At conventional spacecraft speeds, reaching it would take hundreds of thousands of years. No human could survive even a fraction of that journey. But at 99% of light speed, with a gamma factor of 7.1, the picture changes entirely. From Earth's perspective, the trip still takes about 25 years, because nothing can move faster than light. But for the traveler, time dilation compresses that journey by a factor of 7. The subjective journey drops to roughly 3.5 years. You could travel to Vega, spend time exploring any planets orbiting that bright blue-white star, and return to Earth having aged only 7 years, while 25 years have passed at home. If you push the speed to 99.9% of light speed, the numbers become even more striking, with Gamma at about 22. That same 25-year journey shrinks to just over 1 year of experience time. You could travel to Vega and return before reaching your 2nd year on board the ship. Meanwhile, Earth would age 50 years, while you age only 2. Now consider the Pleiades. That familiar cluster of bright blue stars visible to the naked eye in winter skies. It lies about 440 light-years from Earth. At conventional speeds, reaching it would take millions of years, but at 99.9% of light speed, with Gamma above 70, the experienced journey time falls to around 6 years. You could visit one of the most well-known star clusters in human history, explore several star systems within it, and return having aged perhaps 15 years. While nearly 900 years pass on Earth, the center of our galaxy is even farther, about 26,000 light-years away. At its heart lies a supermassive black hole containing around 4 million times the mass of our Sun, surrounded by dense star clusters and extreme environments found nowhere else in the Milky Way. At 99.999% of light speed, with Gamma above 223, the experienced journey time drops to about 116 years. That is still longer than a human lifetime, but it begins to approach the limits of what might be possible for extended missions or future life extension technologies. If speed increases even further, to 99.999% of light speed, with gamma exceeding 700, the galactic center becomes reachable in roughly 37 years of ship time. A traveler could leave Earth at the age of 25, journey to the black hole at the center of the galaxy, and arrive at the age of 62. Returning home, they would find that more than 52,000 years had passed on Earth, while they themselves had lived a normal human lifespan. And then there is Andromeda, the nearest major galaxy, located about 2.5 million light-years away. With its trillion stars forming a vast spiral larger than our own galaxy, it may contain countless worlds, and perhaps even other forms of life. No conventional drive system could ever bridge such a distance within any meaningful time frame. But at velocities where gamma reaches 1 million, at speeds so close to light that the difference becomes almost abstract, the experienced journey time to Andromeda drops to about 2.5 years. A traveler could cross the space between galaxies, explore an entirely different galaxy, and experience the trip as lasting less time than a typical degree program. Meanwhile, Earth would age 2.5 million years. Human civilization might be unrecognizable or gone entirely, and yet the traveler would have aged only a few years. These results reveal something profound hidden within Einstein's equations. The universe does not strictly forbid exploration across vast distances. Time dilation provides a way for a human lifetime to span distances that light itself takes millions of years to cross. The true limitation is not physics, but our ability to build the technology required. We simply do not yet have the technology to reach those required velocities. But this leads to a deeper question. Why do such extreme speeds demand such extraordinary amounts of energy? The answer comes from another of Einstein's profound insights. Captured in perhaps the most famous equation in physics, E equals mc squared tells us that mass and energy are not separate things, but two forms of the same underlying reality. This equivalence has important consequences for anything trying to move at relativistic speeds. As an object accelerates, it gains kinetic energy. At low speeds, this increase follows the familiar rules described by Isaac Newton. If you double your velocity, your kinetic energy increases by a factor of 4. This relationship is simple and, in principle, places no strict upper limit on speed, as long as enough energy is available. But as velocity approaches a meaningful fraction of the speed of light, the situation begins to change. The energy required for further acceleration starts rising far more quickly than Newton's equations would suggest. The object begins to behave as if its mass is increasing. This effect, known as relativistic mass increase, becomes more significant as speed grows. At half the speed of light, an object behaves as though it has about 15% more mass than when at rest. The additional energy used for acceleration seems to go into this growing resistance rather than producing the same gains in speed. By the time you reach 90% of the speed of light, the effective mass has more than doubled. The same thrust that once produced strong acceleration now results in much smaller changes in velocity, as if the spacecraft has become far heavier. At 99% of light speed, the effective mass increases by a factor of 7. At 99.9%, it exceeds 22. Each step closer to the speed of light demands not just more energy, but exponentially more. The same gamma factor that allows time to slow down for the traveler also works against them here, making further acceleration increasingly difficult. This is why the speed of light becomes an absolute limit for any object with mass. As velocity approaches the speed of light, the effective mass tends toward infinity, and accelerating something with infinite mass would require infinite energy. Since infinite energy is not physically possible, reaching the speed of light itself remains forever out of reach. You can move closer and closer, adding more nines to your speed as a fraction of light speed. But you can never quite arrive. The practical energy demands of relativistic travel are almost beyond comprehension, even at speeds well below the theoretical limit. Imagine accelerating a small probe with a mass of about 1,000 kilograms to 90% of the speed of light. The kinetic energy required would exceed 10 to the power of 19 joules, written out in full. That number contains 20 digits. It is roughly equal to the total energy output of the Sun over 2 seconds, or the entire energy consumption of human civilization over about 1 million years, all used to accelerate a single small spacecraft. For a vessel capable of carrying human life, the mass would likely be closer to 100,000 kilograms or more. The energy requirement scales accordingly. To accelerate such a spacecraft to 90% of light speed would require energy comparable to the Sun's total output over several minutes. This is not a limitation of engineering waiting to be solved. It is a fundamental requirement imposed by the structure of spacetime itself. And the situation becomes even more demanding when you consider that travelers would need to slow down upon arrival. Decelerating from 90% of light speed requires the same amount of energy as accelerating to it. A round trip doubles the total requirement. A journey to Vega and back at this speed would demand roughly 4 times the energy needed for a one-way trip, exceeding the Sun's total output over many minutes. These immense energy requirements explain why relativistic travel remains purely theoretical. Even though the physics behind it has been understood for more than a century, engine system humanity has built, tested, or seriously proposed can deliver energy on this scale. Chemical rockets fall short by many orders of magnitude. Nuclear fission improves the situation slightly, but remains far from sufficient. Even nuclear fusion, the same process that powers the Sun, struggles to provide the energy density needed for practical relativistic travel. There are also limits related to how humans can endure acceleration. A continuous acceleration equal to Earth's gravity feels natural and could, in principle, be sustained for long periods. Under these conditions, travelers could move, eat, and function normally throughout the journey. Higher accelerations, however, quickly become problematic. 2 times Earth's gravity leads to fatigue and strain. 5 times can cause loss of consciousness. 10 times can be fatal. If a spacecraft maintained a constant acceleration of 1 Earth gravity, it could reach 90% of light speed in about 11 months. During the first half of the journey, it would accelerate toward its destination. At the midpoint, the spacecraft would rotate and begin decelerating at the same rate, arriving with no relative velocity. This constant acceleration approach changes how we think about travel time. Instead of accelerating quickly and then coasting, the spacecraft spends the entire journey either speeding up or slowing down, maintaining a steady and continuous thrust throughout. For shorter journeys, this method actually requires more energy than a simple coast phase would. But over very long distances, constant acceleration can save time by maintaining thrust instead of drifting at a fixed speed. With 1 year of continuous acceleration at 1 Earth gravity, a spacecraft could reach about 77% of the speed of light. After 2 years, it would approach 97%. After 3 years, it would exceed 99%. As the speed gets closer to light speed, each additional year of acceleration produces smaller gains, but time dilation begins to compensate, reducing the experienced duration of the journey even as acceleration becomes less effective. This leads naturally to one of the most famous consequences of relativity, often called the twin paradox. It illustrates just how deeply time dilation can reshape human experience. Imagine two identical twins, Alice and Bob. Alice boards a relativistic spacecraft and travels to a star 20 light-years away at 90% of the speed of light, while Bob remains on Earth. From Bob's perspective, the journey takes about 22 years each way. He waits 44 years in total, aging from early adulthood into old age. From Alice's perspective, the journey feels very different. At this speed, gamma is about 2.3. So time on board is compressed. Each leg of the journey feels like only 9.5 years. The entire trip takes her about 19 years. When she returns, Alice has aged 19 years, while Bob has aged 44, though they were born at the same time. They are now separated by 25 years of biological age. Alice may just be entering midlife, while Bob is approaching the end of his. This result once seemed deeply puzzling. If motion is relative, why does Alice age less rather than Bob? From her point of view, it could appear that Bob was the one moving away and coming back. The answer lies in the difference between their experiences. Alice undergoes acceleration when her spacecraft changes direction, while Bob remains in a single inertial frame. This asymmetry breaks the apparent symmetry between them and determines which twin ages less. This is not just a thought experiment. It has been tested with real measurements. In 1971, physicists Joseph Hafele and Richard Keating flew cesium atomic clocks around the world on commercial aircraft. Comparing them to identical clocks that remained on the ground, the moving clocks differed by about 270 nanoseconds, exactly as predicted by relativity. The effect is extremely small because airplane speeds are insignificant compared to the speed of light, but it is real, measurable, and it confirms Einstein's predictions made more than a century ago. And once we move into relativistic speeds, time dilation opens up possibilities that go far beyond simple differences in aging. Information from Earth could still reach travelers during their journey, allowing them to receive news, entertainment, and personal messages from home. But this information would arrive in a compressed form. Years of broadcasts from Earth could be received within just months of ship time, meaning travelers could watch decades of history unfold while they are still in transit, seeing entire lifetimes pass in what feels like accelerated time. Communication in the other direction becomes far more limited. Messages sent from the spacecraft would take years, sometimes decades, to reach Earth, and replies would take just as long to return. A traveler moving at 99% of the speed of light toward a star 100 light-years away might experience the journey in about 14 years. But a message sent only 1 year into the trip would not reach Earth until decades later. And any reply would arrive long after the traveler had already reached their destination. The visual experience of such a journey would be equally unfamiliar. Light coming from the direction of travel becomes blue-shifted, its frequency increased by the Doppler effect caused by the spacecraft moving toward it. Stars ahead would shift from their normal colors into blue, then ultraviolet, and eventually into X-ray wavelengths as speed increases. Constellations we recognize would fade from visible light, becoming detectable only with specialized instruments. Light from behind behaves in the opposite way. It becomes redshifted, stretched to longer wavelengths. Stars behind the spacecraft would shift from visible light into infrared, then into radio waves, and eventually disappear entirely as their signals fall below detectable levels. Another effect, known as relativistic aberration, alters the entire field of view. Light from the sides appears to bend forward, compressing the visible universe into a narrowing cone ahead of the spacecraft. At 90% of light speed, most of what you can see would be concentrated within a circle of about 60 degrees in front of you. At 99%, this shrinks to around 16 degrees. At even higher speeds, Nearly the entire universe collapses into a single bright point ahead, with darkness stretching behind. Even the empty space between stars becomes dangerous at these velocities. The interstellar medium is not completely empty. Each cubic centimeter contains, on average, about one hydrogen atom, along with traces of other particles. At low speeds, this poses no problem. Spacecraft pass through it almost without noticing. But at relativistic speeds, these sparse particles become a serious threat. Each hydrogen atom striking the spacecraft carries energy that increases with the square of the gamma factor. At 90% of light speed, each impact is comparable to a high-energy cosmic ray. At 99%, the energy increases by another factor of about 20. The front of the spacecraft would be constantly bombarded by these high-energy particles, capable of damaging electronics, eroding materials, and penetrating biological tissue. Protecting against this environment would require either extremely heavy shielding or advanced systems to deflect incoming particles before they make contact. Magnetic fields could, in principle, deflect charged particles away from the spacecraft. But the required field strength increases rapidly with velocity. Physical shielding is another option, though it adds mass, and that mass must also be accelerated to relativistic speeds, further increasing the energy demands. Despite all these challenges, the physics of relativistic travel is well understood and has been confirmed through observation. Time dilation is not just a theoretical idea. It has been measured and verified through decades of precise experiments. The equations show that travel across interstellar and even intergalactic distances within a single human lifetime is allowed by physics. The true obstacle is not the laws of nature, but our ability to build the necessary engine system. So what kind of technology could actually reach these extreme velocities? What engines could provide the enormous energy required? To answer that, we have to explore different drive systems that attempt to turn these theoretical possibilities into reality. From nuclear explosions to antimatter reactions, and even beams of light pushing delicate sails through space. The gap between our current spacecraft speeds and those required for meaningful interstellar travel is almost beyond comprehension. Our fastest probes move at only about 1/10,000th of the speed of light. Noticeable relativistic effects begin around 10% of light speed and become truly significant only above 90%. Bridging this gap demands spacecraft drive systems far beyond anything humanity has built, tested, or even fully designed. To understand the scale, consider that the Parker Solar Probe reaches only about 0.06% of light speed at its fastest. To reach 10% of light speed would require increasing that velocity by roughly 170 times. To reach 90% of light speed, where time dilation dramatically reshapes travel, would require speeds about 1,500 times greater than what we can currently achieve. This is not a small step forward. It represents a complete transformation in propulsion technology, spanning multiple orders of magnitude. Even so, scientists have imagined concepts that could begin to close this gap. Some rely on extending known physics through advanced engineering. Others require breakthroughs in materials, energy generation, or entirely new approaches. A few venture into areas where the physics itself is still uncertain. Together, they outline both the possibilities and the limits of interstellar travel within a human lifetime. Among these ideas, nuclear pulse propulsion stands out as one of the most extreme ever seriously studied. It emerged in the late 1950s at General Atomics in San Diego, where a group of physicists considered a question that seemed almost unthinkable. What if spacecraft propulsion could be powered by nuclear explosions instead of containing that energy within a reactor? What if you detonated a series of devices behind the spacecraft and used the force of those blasts to push it forward toward the stars? This concept, known as Project Orion, attracted some of the most capable scientific minds of its time: Freeman Dyson, Theodore Taylor, and many other physicists and engineers spent years turning this seemingly impossible idea into detailed engineering designs. They were not imagining science fiction. They were conducting careful calculations, building models, and testing whether such a system could actually work. The core concept of Orion was surprisingly direct. The spacecraft would carry a large number of nuclear explosive devices, specially designed for propulsion. These would be released one by one from the rear of the craft and detonated at precise distances. Each explosion would create a rapidly expanding plasma fireball, spreading outward in all directions. At the back of the spacecraft, a massive pusher plate would absorb part of this energy. The impact of the plasma would push the vehicle forward. Between the pusher plate and the crew section, a system of shock absorbers would smooth out these repeated blasts, turning violent impacts into a more manageable and continuous acceleration. The Orion team even tested this idea using conventional explosives. They built small-scale models with pusher plates and detonated charges beneath them. The results were clear. The models lifted off. The plates withstood repeated impact. The shock absorption systems behaved as expected. The program was ultimately halted in 1963 due to nuclear test ban treaties before full-scale nuclear tests could take place. But by that point, the underlying physics had already been demonstrated. Calculations suggested that Orion could outperform any rocket engine systems imagined at the time, and even many proposed since. A relatively modest design using nuclear fission devices could reach speeds of about 3 to 4% of the speed of light. More advanced versions using fusion-based explosives might achieve 8 to 10%. The most ambitious concept, requiring technology beyond what was available in the 1960s, could potentially reach 15% of light speed or more. At 10% of light speed, a journey to Tau Ceti, a star about 12 light-years away that may host habitable planets, would take roughly 120 years. This is still longer than a human lifetime, but it begins to approach the limits of what might be possible for multi-generational missions, or for travelers willing to spend most of their lives in transit. At these speeds, time dilation provides only a very small benefit, reducing the journey time by less than 1%. From the traveler's perspective, the trip would feel almost the same as it would to observers on Earth. The engineering challenges remain significant, but not beyond imagination. The pusher plate would need to endure repeated exposure to nuclear fireballs, with temperatures reaching millions of degrees in rapid pulses occurring thousands of times. However, materials science has advanced considerably since the 1960s. Modern composites and heat-resistant metals may be capable of handling such conditions. The shock absorption system would also need to convert intense bursts of force into smooth acceleration without damaging the spacecraft or harming its occupants. Even this appears solvable with sufficient engineering effort. Carrying thousands of nuclear devices introduces serious risks, both during launch and throughout the mission. A failure during departure from Earth could spread radioactive material across vast regions. An accident in space could end the mission instantly. And yet, nuclear pulse system does not rely on unknown physics or speculative materials. It is based on principles we already understand and technologies that are, at least in theory, within reach. In that sense, it may represent one of the most realistic near-term paths toward interstellar speeds. A later study known as Project Longshot, conducted by the United States Naval Academy in the late 1980s, explored a refined version of this idea using fusion instead of fission. Rather than atomic bombs, it proposed using small fusion explosions. increasing efficiency while reducing radioactive risks. The long-shot design aimed to reach Barnard's star, about 6 light-years away, in roughly 100 years, traveling at a few percent of the speed of light. The study concluded that such a mission could be technically feasible with technology developed over the coming decades. Antimatter propulsion, however, exists in a completely different category. It offers an energy density far beyond any other known fuel, while still remaining grounded in established physics. When matter meets antimatter, both are completely converted into energy. 100% of their combined mass is released. This is vastly more efficient than nuclear fission, which converts only a tiny fraction of mass into energy. Or fusion, which improves on that, but still falls far short. Antimatter is roughly 100 times more energy dense than fusion, and about 1,000 times more efficient than fission. Just 1 gram of antimatter annihilating with 1 gram of normal matter would release around 180 trillion joules of energy. That is comparable to the explosive energy of an atomic bomb, and enough to power an average household for several years. With that level of energy, even a small spacecraft could reach speeds far beyond what chemical rockets could ever achieve. This extraordinary energy density makes antimatter an ideal candidate, in theory, for reaching relativistic velocities. An antimatter engine would generate thrust by directing the products of annihilation through magnetic field. When an electron meets its antimatter counterpart, a positron, both disappear and release high-energy gamma radiation. When protons encounter antiprotons, the reaction produces particles called pions, which can be guided using magnetic fields. These particles then decay into lighter forms, such as muons, and eventually into electrons and neutrinos. By channeling these products, the engine could produce exhaust moving at a significant fraction of the speed of light, far exceeding anything achievable with chemical, nuclear, or even fusion propulsion. This extremely high exhaust velocity changes the rocket equation that so tightly limits chemical propulsion. With antimatter, reaching relativistic speeds becomes mathematically possible. Instead of requiring more fuel than exists in the observable universe, consider a journey to Epsilon Eridani, a young star similar to our Sun located about 10 to 12 light-years from Earth, known to host at least one planet. At around 30% of the speed of light, which might be achievable using roughly 100 kilograms of antimatter for a small probe. The journey would take about 35 years from Earth's perspective. At that speed, time dilation would reduce the traveler's experience to around 33 years. A modest difference, but still meaningful. A person leaving Earth at the age of 30 could arrive at Epsilon Eridani at around 63, still capable of carrying out exploration. If larger amounts of antimatter were available, higher speeds become possible, with several thousand kilograms. A spacecraft could in theory reach 70 to 80% of light speed. At those velocities, the journey would still take around 13 to 14 years from Earth's perspective. But the traveler would experience only 8 or 9 years. What once seemed like a lifetime-long journey becomes something closer to a long expedition. The true obstacle, however, is not the physics. It is production. Antimatter does not naturally exist in usable quantities anywhere in the known universe. Every antiproton must be created in particle accelerators, a process that consumes enormous amounts of energy. Today, total global production amounts to only about 10 to 20 nanograms per year, generated at facilities such as CERN in Switzerland and Fermilab in the United States. To understand how small this is, consider that producing 100 kilograms of antimatter at current rates would take roughly 5 billion years. The energy cost makes the problem even more severe. Creating antimatter requires about 10 billion times more energy than the antimatter itself ultimately contains. Producing enough fuel for even a single interstellar mission would demand energy far beyond the total consumption of human civilization over centuries, possibly even millennia. Storing antimatter presents another challenge. It annihilates instantly upon contact with normal matter, so it must be suspended in a perfect vacuum using magnetic fields, never touching any physical surface. The fuel must never come into contact with the container walls, must remain stable during the intense vibrations of launch, and must survive for decades throughout an interstellar journey. So far, the longest antimatter has been stored is about 16 hours. Achieved at CERN in 2023, extending that to decades would require an improvement of roughly 10,000 times. Because of these challenges, antimatter drive remains far in the future. If it becomes practical at all, the physics behind it is elegant and well understood. But the engineering is far beyond what we can currently achieve. In many ways, antimatter serves more as an ideal benchmark, a theoretical limit against which other drive systems can be compared. Rather than a realistic path to the stars in the near term, beamed energy drive offers a different approach. Avoiding one of the core problems of traditional rockets, conventional spacecraft must carry their own energy source, and that energy source has mass, which must also be accelerated. This creates a cycle where adding fuel to go faster also makes the spacecraft heavier, requiring even more fuel. Beamed energy systems break this cycle by keeping the power source at the origin. The idea dates back to the 1960s, when physicist Robert Forward proposed using powerful lasers to push lightweight sails to extremely high speeds. In this concept, the spacecraft carries no fuel at all, instead gaining momentum by reflecting photons from an external energy source. With sufficiently powerful lasers and extremely lightweight sails, it becomes possible, at least in theory, to reach a significant fraction of the speed of light. One of the most serious modern efforts in this direction is the Breakthrough Starshot project, announced in 2016 with initial funding of $100 million from Yuri Milner and supported by Stephen Hawking. The concept involves using a ground-based array of lasers to accelerate tiny spacecraft, often called star chips, to about 20% of the speed of light. At that speed, a journey to the Alpha Centauri system would take roughly 20 years. The design envisions a network of lasers producing around 100 gigawatts of power, comparable to the output of 100 large nuclear power plants. This energy would be focused onto a spacecraft weighing only a few grams, consisting of a reflective sail, perhaps 4 meters wide, attached to a miniature chip carrying cameras, communication systems, and navigation equipment. The pressure from the laser light would accelerate this delicate structure from rest to 20% of light speed in just 10 minutes. The technical challenges are immense, but not necessarily impossible. The laser array must maintain precise focus on a rapidly accelerating target. Even as the distance grows and communication delays increase, the sail must withstand radiation levels that would destroy most known materials, requiring highly advanced reflective coatings. And the tiny onboard system must remain functional despite being smaller than a paperclip. Even so, this approach has clear advantages. The energy source remains on Earth, where it can be maintained, upgraded, and reused. Each individual spacecraft is relatively inexpensive, allowing many to be launched, increasing the likelihood that some will survive and send back data. However, there is a fundamental limitation when it comes to human travel. A laser-pushed sail can accelerate by reflecting light from behind, but it cannot easily slow down. Since there is no corresponding laser at the destination, A probe using this method would pass through the Alpha Centauri system at high speed, with only minutes to collect data before continuing into deep space, never to return. For robotic probes that only need to capture images, this limitation may be acceptable. But for human travelers who need to slow down and explore, it becomes a critical problem. One possible solution is the concept of a magnetic sail. This system uses a large superconducting loop to generate a powerful magnetic field, which interacts with charged particles in the interstellar medium or with the stellar wind near a destination star. This interaction creates drag, gradually slowing the spacecraft over time. In principle, a magnetic sail could reduce a relativistic spacecraft to rest over months or years. The physics behind this idea is sound, but the engineering becomes extremely challenging at high speeds. Slowing down from even 20% of the speed of light requires dissipating enormous amounts of kinetic energy. This would heat the magnetic sail and surrounding structures to extreme levels. The superconducting systems must remain stable despite this heating, requiring advanced thermal control. At the same time, the density of the interstellar medium varies along different paths, making it difficult to predict and control the deceleration process. Fusion drive offers a more grounded path towards speeds where time dilation begins to matter. Fusion reactions combine light atomic nuclei, typically isotopes of hydrogen, releasing far more energy than chemical or fission reactions. The Sun itself operates this way, converting hydrogen into helium and producing the energy that sustains life on Earth. If we could harness fusion for propulsion, it could open a realistic path toward interstellar travel. The physics is well understood. When deuterium and tritium fuse, they produce helium and a high-energy neutron, releasing about 17.6 million electron volts of energy per reaction. This is vastly greater than the energy released in chemical reactions. A fusion-powered rocket could, in theory, achieve exhaust velocities of 3 to 5% of the speed of light, allowing spacecraft to reach 10 to 15% of light speed with reasonable fuel requirements. One of the most detailed studies of this idea was Project Daedalus, conducted by the British Interplanetary Society between 1973 and 1978. The design proposed a two-stage spacecraft using pellets of deuterium and helium-3, ignited through inertial confinement fusion. Powerful electron beams would compress these fuel pellets until fusion occurred, and the resulting energy would be directed through a magnetic nozzle to produce thrust. Daedalus was designed to reach Barnard's star, about 6 light-years away, in roughly 50 years. Traveling at around 12% of light speed, the first stage would operate for about 2 years, accelerating the spacecraft to just over 7% of light speed before separating. The second stage would continue accelerating for nearly 2 more years, reaching final velocity before coasting toward its destination. The spacecraft would be enormous, with a launch mass of around 54,000 tons, most of it fuel. It would not slow down upon arrival, instead passing through the Barnard star system at high speed, collecting data during a brief encounter before continuing into deep space. Later work, such as Project Icarus, began in 2009, revisited these ideas with updated technology and improved models. These studies generally suggest that speeds between 10 and 20% of light speed may be achievable with advanced fusion drive technology offers within the next century. At around 15% of light speed, a journey to Sirius, located about 8.6 light-years away, would take approximately 57 years from Earth's perspective. Time dilation at this speed provides only a small benefit, reducing the experience time by about 1%. A traveler leaving Earth at 25 would arrive in their early 80s, having spent nearly their entire adult life in transit. This represents survival, but not truly practical interstellar travel. To reach speeds where time dilation becomes genuinely useful, motion must go beyond conventional fusion. One idea, proposed by physicist Robert Bussard in 1960, offered an elegant solution. Instead of carrying fuel, the spacecraft would collect hydrogen directly from the interstellar medium using vast magnetic fields, then fuse that material to produce continuous thrust. In theory, such a Bussard ramjet could accelerate indefinitely, gathering fuel as it traveled and limited only by relativistic effects as it approached the speed of light. The concept inspired both scientific research and decades of science fiction, appearing to offer a way around the fuel limitations that constrain traditional rockets. However, more detailed analysis revealed serious problems. The interstellar medium contains, on average, only about 1 hydrogen atom per cubic centimeter, sometimes less, sometimes more. To collect enough fuel, the magnetic scoop would need to extend thousands of kilometers across, but this same structure would also interact with incoming particles, creating drag that outweighs the thrust produced by fusion. In effect, the ramjet becomes a kind of parachute, generating more resistance than forward motion. Later studies suggested it might function in unusually dense regions of space, such as molecular clouds, but not in the typical conditions between stars. With our current understanding of physics, continuous acceleration through fuel collection appears unworkable. This has led to hybrid approaches that combine multiple drive methods. A spacecraft might use nuclear pulse drive to gain initial speed, then deploy a magnetic sail to slow down upon arrival. Another possibility is to use a laser-driven sail for early acceleration, followed by an onboard fusion system for deceleration and maneuvering. Imagine la mission to Toseti, about 12 light-years away. With several candidate planets that could potentially support life, the journey begins with a powerful laser array pushing against a sail attached to a fusion-powered spacecraft, accelerating it to around 15% of the speed of light within the first week. After this initial phase, the spacecraft would coast for roughly 80 years, before activating its fusion engines to slow down as it approaches the destination, eventually entering orbit around the target star. This approach reduces the amount of fuel carried on board, since the acceleration phase is handled externally, while still allowing the spacecraft to decelerate and explore rather than simply pass through. Even so, the total journey time of about 80 years still exceeds a typical human lifespan. A crew departing in their 20s might live to see arrival in extreme old age, assuming future advances in medicine extend human life. Beyond this, more speculative ideas begin to explore regions of physics that remain uncertain or entirely theoretical. The Alcubierre warp drive, proposed by Mexican physicist Miguel Alcubierre in 1994, describes a way space-time itself could be shaped to allow effective, faster-than-light travel without breaking the laws of relativity. The idea is not to move a spacecraft through space, but to contract space in front of it and expand space behind it, creating a kind of bubble that carries the vessel forward. Inside this warp bubble, the spacecraft would remain at rest relative to its local space-time. No speed limit is violated because it is not moving in the usual sense. Instead, space itself is doing the moving. In principle, destinations that would take light years to reach could be accessed in much shorter times, depending on how strongly space-time is distorted. The mathematics behind the Alcubierre drive is consistent with general relativity. It describes a configuration that, while highly unusual, does not break known physical laws. But there is a critical problem. Creating such a structure appears to require negative energy density, something that may not exist in usable amounts in nature. Even the most optimistic estimates suggest energy requirements comparable to the mass energy of Jupiter. More conservative calculations push that requirement beyond the total mass energy of the observable universe. For now, the warp drive remains a fascinating mathematical possibility with no clear path to reality. Wormholes offer another speculative route, potentially bypassing the need for high speeds altogether. These hypothetical structures would connect distant regions of space-time through a shortcut, allowing a traveler to move between them without crossing the intervening distance in the usual sense. Enter one end, and you could emerge light years away almost instantly. But stable, traversable wormholes also appear to require exotic matter with negative energy density to keep them open. Whether such matter can exist in sufficient quantities is still unknown. Some theories suggest tiny amounts might be produced through quantum effects, but scaling this up to something usable remains entirely uncertain. Even if wormholes could be created, they introduce another difficulty. One end of the wormhole would still need to be transported to its destination. If that requires conventional travel at sublight speeds, then the original problem has not truly been solved. Returning to ideas grounded in established physics, the most realistic frontier likely lies with advanced fusion systems, possibly combined with beamed energy for initial acceleration. These approaches could, in principle, reach speeds of around 15 to 20% of light speed within the next century. Assuming sustained progress, at 20% of light speed, time dilation becomes measurable but still modest. The gamma factor is about 1.02, meaning that 50 years on Earth would feel like roughly 49 years on board the spacecraft. The traveler gains about 1 year over the course of the journey. It is enough to notice, but not enough to fundamentally change the experience of interstellar travel. Truly transformative time dilation would require velocities far closer to the speed of light, pushing us once again to the edge of what physics allow and what technology might one day achieve. Reaching speeds above 50% of light speed, and ideally beyond 90%, would require major advances in drive systems that we cannot yet fully design. Even in theory, the gap between 20% and 90% of light speed may be one of the greatest challenges in all of physics. No existing technology, and no realistic fuel source we understand today, can bridge that divide. And yet, the laws of physics do not forbid such travel. The equations allow velocities arbitrarily close to the speed of light, limited only by the energy available. Time dilation is real, and it does compress journey times for the traveler, turning distances that once seemed impossible into something merely extremely difficult. The universe has not placed a hard barrier against interstellar exploration. It has simply set the cost extraordinarily high. Whether humanity will ever develop the technology needed to reach these velocities remains uncertain. The engineering obstacles are immense, and the energy demands exceed our current capabilities by margins that are difficult to fully grasp. The development timescale would likely span generations, requiring a level of continuity and commitment that few civilizations have ever sustained. But the physics itself is clear. With sufficient speed, a single human lifetime could stretch across distances that light would take thousands or even millions of years to cross. Now imagine a future where drive systems have effectively no limits. Energy is abundant. Acceleration to extreme velocities is routine. Spacecraft can reach speeds such as 99.999% of light speed without difficulty. In that case, what becomes the true limit of how far a human could travel? At that point, the answer no longer depends on engineering, but on the structure of the universe itself. Even with near-perfect drive systems, there are boundaries that cannot be crossed. These limits are built into space-time, shaped by the expansion of the cosmos, and constrained by the finite age of the universe. They define the maximum reach of any traveler. No matter how advanced their technology or how long they live, To understand these limits, we must look beyond drive systems and consider the large-scale behavior of the universe itself. The universe is not static. It expands, stretching over time and carrying galaxies apart. Much like raisins drifting away from each other in rising dough, this expansion creates horizons, regions beyond which no traveler can ever reach. Regardless of speed or duration, the observable universe gives us a first reference point. It is a sphere centered on Earth, extending about 46.5 billion light-years in every direction. It contains all the light that has had time to reach us since the beginning of the universe. Its total diameter is roughly 93 billion light-years. Within this immense volume, there are around 2 trillion galaxies, each containing hundreds of billions of stars, many of which may host planets where life could arise. At first glance, this observable region might seem like the ultimate boundary of exploration. Beyond it, we have detected nothing, and perhaps nothing can ever be reached. No telescope, no radio antenna, and no gravitational wave detector has ever captured a signal from beyond the observable horizon. In a very real sense, this boundary defines everything we can ever observe. But what we can observe is not the same as what we can reach. And that difference becomes crucial when we think about traveling across the cosmos. The light we receive today from the most distant galaxies began its journey more than 13 billion years ago, when the universe was far younger and much smaller. During that time, space itself has expanded, stretching the distance between those galaxies and Earth. Objects that emitted light billions of years ago are now tens of billions of light-years away, carried outward by this ongoing expansion. And this expansion is not slowing down. In 1998, 2 independent teams studying distant supernovae discovered that the expansion of the universe is accelerating. This acceleration is driven by something we call dark energy, which makes up about 68% of the total energy in the universe. As a result, distant galaxies move away from us faster and faster over time. This discovery, which earned the Nobel Prize in Physics in 2011, changed how we understand the fate of the cosmos. It also introduces a deeper boundary than the observable horizon. The Hubble sphere marks the distance at which the expansion of the universe matches the speed of light. At this boundary, roughly 14 billion light-years from Earth, galaxies recede at about 186,000 miles per second. This does not break the rules of relativity, because the galaxies are not moving through space faster than light. Instead, space itself is expanding, carrying them along, much like objects drifting apart on a swelling surface. But for a traveler, the distinction offers little comfort. Whether objects are moving through space or being carried by it, anything beyond this boundary is receding faster than any signal or spacecraft could catch up to. Light emitted today from galaxies just beyond this limit will never reach us. Each photon moves forward, but the space it must cross expands even faster, preventing it from ever arriving. These signals travel endlessly through an ever-growing universe, never reaching any observer. And yet, this is not quite the final limit. There is an important difference between light and a spacecraft. A photon moves at a constant speed from the moment it is emitted. It cannot accelerate. A spacecraft, in contrast, can continue to accelerate, gradually increasing its speed. Because of this, a sufficiently advanced spacecraft could, in principle, push outward against the expansion locally, moving into regions that light emitted from Earth today could never reach. The cosmological event horizon defines the true boundary of what can ever be reached. This horizon, currently about 16 to 17 billion light-years from Earth, marks the farthest distance any signal or traveler leaving today could ever hope to reach. Even given unlimited time, beyond this limit, the expansion of space has already outpaced any possible journey. Space itself is stretching so rapidly that no amount of speed could overcome it. Destinations beyond this horizon are not simply difficult to reach. They are fundamentally unreachable under the laws of physics as we understand them. The existence of this boundary comes from how the universe expands over time, especially as dark energy continues to drive that expansion faster and faster, and this boundary is not fixed. It slowly contracts. Regions that are reachable today will eventually slip beyond this horizon, carried away by the accelerating expansion. In that sense, the universe is not only vast, but also slowly closing its doors. The opportunity for exploration becomes smaller with time. Current models suggest that in about 100 billion years, the event horizon will shrink to include only our local group of galaxies, Andromeda, which is already moving toward us. Will merge with the Milky Way long before that happens. But beyond this merged system, every other galaxy will have disappeared beyond reach, on even longer timescales, measured in trillions of years. This isolation becomes complete. Future astronomers, living in whatever galaxy forms from that merger, will see a universe containing only their own stars. No distant galaxy will be visible. Even the faint afterglow of the Big Bang will have stretched beyond detection. All evidence of the wider universe will be gone. Those future observers might never realize that billions of galaxies once existed. They may conclude that their galaxy is the entire universe, unaware that cosmic expansion has erased the evidence. This creates a kind of countdown for exploration. Every galaxy, every cluster, every distant structure we might dream of reaching has a limited window before it becomes permanently inaccessible. The universe offers an opportunity to explore, but that opportunity is slowly fading. Within these limits, we can ask a more personal question. How far could a single human lifetime actually reach? To answer this, we must combine time dilation with the expansion of the universe. Considering not only how far we travel, but how the destination itself moves during that journey. At 99% of the speed of light, a traveler maintaining that velocity for 50 years of experience time would cross roughly 350 light-years. During that same period, Earth would age about 355 years. For the traveler, it is only half a century. That distance includes tens of thousands of star systems, many of them similar to our Sun, and many known to host planets. Within that range are regions where stars are still forming. Ancient clusters filled with some of the oldest stars in the galaxy, and a wide variety of stellar environments very different from our own. If the speed increases to 99.9% of light speed, the scale changes dramatically. With a gamma factor above 22, 50 years on board corresponds to more than 1,000 years on Earth. In that time, the traveler could cover around 1,100 light-years. That region contains millions of stars and potentially billions of planets where conditions might allow life. Distances that once seemed unreachable begin to fall within the span of a single lifetime. At least from the traveler's point of view, the Orion Nebula, one of the most striking stellar nurseries visible from Earth, lies about 1,300 light-years away. At 99.9% of the speed of light, a traveler could reach this region, observe new stars forming, watch protoplanetary disks slowly gathering into planet, and experience one of the most vivid environments in our galaxy. All within a single lifetime. They would arrive having aged 50 years, while more than 1,000 years passed on Earth. And yet, even this is only the beginning. At 99.99% of light speed, gamma rises above 70. At this level, distances expand dramatically. Regions like the Carina Nebula, around 7,500 light-years away, could be reached in just over a century of ship time. The Eagle Nebula, home to the well-known Pillars of Creation at roughly 7,000 light-years, also becomes accessible within a similar span. Even the center of the Milky Way begins to fall within reach. Sagittarius A star, the supermassive black hole at the heart of our galaxy, containing about 4 million times the mass of the Sun, lies around 26,000 light-years from Earth. At these extreme velocities, a traveler could reach it in roughly 370 years of onboard time. A journey that would require multiple generations, yet still finite. As speeds increase further, the scale becomes almost difficult to comprehend. At 99.999% of light speed, gamma exceeds 223. 50 years of experience time would allow a traveler to cross more than 11,000 light-years, carrying them deep into the structure of the galaxy. Push this even further to 99.9999%, and gamma rises above 700. In 50 years of ship time, a traveler could cross around 35,000 light-years, moving beyond the galactic center and into the far side of the Milky Way. This leads to a remarkable realization. In principle, a person could board a spacecraft, accelerate to extreme relativistic speed, and traverse the entire galaxy, emerging on the opposite side, tens of thousands of light-years away, while experiencing only a fraction of that time personally. With advanced life extension, even a single individual could complete such a journey. At even higher gamma factors, intergalactic travel begins to enter the realm of possibility. The Large Magellanic Cloud, a satellite galaxy of the Milky Way located about 160,000 light-years away, could be reached in about 50 years of ship time if gamma approached several thousand. Meanwhile, Earth would age 160,000 years. The Small Magellanic Cloud, around 200,000 light-years away. The Sagittarius Dwarf Galaxy at about 70,000 light-years. And the Ursa Minor Dwarf Galaxy at roughly 200,000 light-years. All become reachable within extended human timescales at these extreme velocities. Civilizations may rise and fall during such journeys. Entire histories may pass. But for the traveler, the experience could still fit within the span of a lifetime. A traveler willing to spend about 100 years of subjective time in transit could visit multiple dwarf galaxies, exploring stellar populations very different from those in our own galactic disk. And then there is Andromeda, the true test of relativistic travel within our local cosmic neighborhood. At a distance of roughly 2.5 million light-years, it is the nearest major galaxy to the Milky Way, a vast spiral system even larger than our own, containing around 1 trillion stars. Reaching Andromeda would require either unimaginably long journeys at low speeds or extreme relativistic motion, where gamma rises into the tens of thousands. At a gamma of 50,000, 50 years of experienced travel would correspond to a journey of 2.5 million light-years, matching the distance to Andromeda. A traveler leaving Earth at this speed would arrive having aged only 50 years. While Earth itself would have aged 2.5 million years, they would emerge into a completely different cosmic environment, surrounded by unfamiliar stars, orbiting a distant galactic center, with no meaningful connection to their origin. What might they find there? Andromeda contains stars both older and younger than those in the Milky Way. Its central region is larger and more pronounced. At its core lies a supermassive black hole estimated to be about 100 million times the mass of the Sun, far larger than the one in our own galaxy. It is also surrounded by dozens of smaller satellite galaxies, many hosting their own unique stellar populations and planetary systems. Environments unlike anything found near Earth. But there is a cost to such a journey. The traveler could never truly communicate their discoveries back home. Even if signals were sent, they would take 2.5 million years to arrive. The civilization that launched the mission would have disappeared into deep history long before any message could be received. In a very real sense, the traveler would no longer belong to the Milky Way. They would become a resident of Andromeda, permanently separated from their origin. The journey becomes a one-way passage into an entirely different universe of experience. If gamma increases even further, the scale becomes almost cosmological. The Virgo cluster, containing more than 1,300 galaxies and located about 54 million light-years away, becomes reachable at gamma values near 180,000. The traveler would age 50 years, while Earth aged 54 million years. To observers on Earth, the traveler's departure would feel more ancient than the age of the dinosaurs. And yet, for the traveler, it would remain a single lifetime. Even larger structures come into reach. The Coma cluster, around 320 million light-years away, and the Perseus cluster, roughly 240 million light-years distant, represent enormous gatherings of galaxies, bound together by gravity at sufficiently extreme velocities. These too become accessible. A traveler could move between these vast cosmic structures, observing thousands of galaxies, witnessing the architecture of the universe on scales far beyond anything we can directly experience from Earth. At the absolute extreme, where gamma approaches truly immense values, the equation suggests that a single lifetime could span distances approaching the full observable universe. A traveler maintaining a constant acceleration of 1 Earth gravity, then reversing halfway to decelerate, could, in theory, reach the edge of the observable universe in about 45 years of ship time. During that period, they would age 45 years. While the universe outside would have aged on the order of 28 billion years, they would arrive not at the places we see today, but at regions whose light has only just reached us, encountering them after billions of years of cosmic evolution. Yet even such extreme scenarios run into a final boundary set by the expansion of the universe. The cosmological event horizon cannot be crossed. No matter how fast you travel, any destination already beyond roughly 17 billion light-years will remain forever unreachable. Trying to chase such regions only delays the moment when expansion carries them beyond reach entirely. And even targets that are within reach today may not remain so. A traveler heading toward a distant galaxy near this boundary could find that, during the journey itself, cosmic expansion has pushed that galaxy permanently out of reach. In this sense, the reachable universe is not fixed. It slowly shrinks. Even as we attempt to explore it, there is also a deeper consequence to relativistic travel. Time dilation allows you to cross vast distances while aging slowly, but it does not allow you to return to the same moment in history. Every journey becomes a one-way passage into the future. Consider a round trip to the Pleiades, about 440 light-years away, at 99% of light speed. The outward trip would take around 445 years on Earth, but only about 63 years for the traveler. The return journey would take the same. In total, the traveler would age roughly 126 years. While nearly 900 years would have passed on Earth, the world they returned to would be almost unrecognizable. Languages would have changed. Cultures transformed. Technologies advanced beyond anything familiar. They would return not as a contemporary, but as a relic of a distant past, perhaps studied, perhaps admired, but separated from everything they once knew. As distances grow, this separation becomes even more profound. A round trip to the center of the galaxy at 99.99% of light speed would bring the traveler back to an Earth more than 500,000 years in the future. Modern humans have not even existed that long. A journey to Andromeda, if it could somehow be completed and returned, would mean coming back to an Earth 5 million years ahead in time. 5 million years ago, human ancestors had not yet fully separated from other great apes. Whatever beings might exist on Earth after such a span would likely be as different from us as we are from those early ancestors. These scenarios reveal that relativistic travel is not simply faster movement through space, it is a fundamentally different kind of journey. One that carries you not only across distance, but forward through time itself. The journeys of Columbus and Magellan, of Lewis and Clark, even of the Apollo astronauts, all preserved a thread between the traveler and home. Messages could still be sent. Time passed, but not so much that it erased memory. When they returned, there were still people who remembered them. Places that still felt familiar. Distance separated them, but it never truly severed the connection. Relativistic travel changes that completely. It does not just stretch distance, it breaks continuity. A traveler leaving Earth for the stars is not simply going somewhere else. They are leaving their time behind. What they accept is not just a journey, but a kind of irreversible departure from everything they have ever known. They move forward through time, unable to return to the moment they left, and even if they return to the same place in space, the Earth they find will no longer be their home in any meaningful sense. It will share the same orbit, the same continents perhaps, but not the same people, not the same culture, not the same world. This reframes the question entirely. How far can a human travel is no longer just a matter of distance. It becomes a question of what you are willing to leave behind. Range begins to trade against connection. Exploration begins to compete with belonging. Discovery comes at the cost of return. Some travelers might choose to go as far as physics allows, accepting permanent separation from their origin. For them, a single lifetime, measured in their own experience, could span billions of light years. They could reach the most distant galaxies we can currently observe, crossing the universe in a way that once seemed impossible even to imagine. But for those who wish to return, who hope to remain part of a recognizable human story, the limits become far smaller. If you want to come back within a few centuries of Earth time, if you want even a chance that something familiar still exists, then your journey must remain local. Perhaps a few hundred light years, and yet even that small range contains hundreds of thousands of stars and countless worlds, entire systems waiting to be explored. But compared to the scale of the galaxy, and especially the universe, it is only a tiny fragment. And this leads to something deeper. These calculations do not just tell us how far we can go, they reveal something about our place in the cosmos. We exist in a universe that does not confine us by its laws. The physics allows exploration on scales that stretch far beyond intuition. It offers pathways not just to nearby stars, but to distant galaxies, to structures spanning billions of light years. What stops us today is not nature itself, but our current limits in energy, engineering, and imagination. The universe is not a prison. It is a vast landscape with doors that are difficult, but not forbidden, to open. In principle, a single human life, measured by the traveler's own time, could encompass journeys that would once have belonged only to myth. From a small planet orbiting an ordinary star, in an unremarkable corner of one galaxy, a person could travel far enough to witness galaxy clusters containing thousands of galaxies, immense cosmic voids stretching across unimaginable distances, and the vast web-like structure of the universe itself. And perhaps the most remarkable part is this. All of it is allowed, and yet, these same calculations reveal something deeper, not just possibility, but isolation, even with perfect drive systems, even with limitless energy. Most of the universe remains forever beyond our reach. The event horizon is not a wall we can cross. It is a boundary that moves away from us, carried outward by the expansion of space itself. No matter how fast we travel, most galaxies are already gone in a practical sense. We can see them. Their light arrives after journeys lasting billions of years. But we will never touch them, never stand among their stars, never send a signal that reaches them in return. The 2 trillion galaxies we observe are not a map of destinations. They are, in large part, a record of places already lost, perhaps only a tiny fraction. Those within our local cosmic neighborhood remain within reach before expansion carries them away. Everything else exists only as distant light, a memory written across the sky. This does not diminish the significance of reaching the stars, but it places that achievement in a wider perspective. Humanity could one day spread across hundreds, even thousands of light years. We could settle worlds across our region of the galaxy, build a network of civilizations among the stars, and still occupy only a vanishingly small portion of what exists. Even if we filled the entire Milky Way, every star system, every planet, every orbit, we would still be just a single point in an ocean of galaxies stretching beyond comprehension. So the question is no longer simply how far we can go. It becomes something more personal. What kind of journey are we willing to take? Because every destination carries a cost, not just in energy or engineering, but in identity, in connection, in what it means to belong somewhere. A traveler who sets course for Andromeda is not just crossing distance, they are choosing separation. They will never again meet another human from their own time. They will never share their discoveries with the civilization that made their journey possible. They become something new, not an explorer returning home, but the beginning of a different branch of humanity, planted in a distant galaxy, disconnected from its origin. And perhaps that is enough. Perhaps there is meaning in that act alone, in knowing that human awareness has crossed into another galaxy, that the universe is being experienced from more than one place. Or perhaps something else matters more. Perhaps the value of exploration is not just in seeing, but in sharing, in returning, in telling the story. In that case, the most meaningful journeys may not be the farthest ones, but the ones that allow us to remain connected, to explore, and still come home. There is no single answer, only a spectrum of choices, shaped by what we value most. Different travelers will choose different paths. Some will look outward, toward the fading edge of the observable universe, drawn by the quiet promise of distance itself. Others will remain closer to home, choosing journeys that still allow a return, where the thread between departure and arrival is not entirely broken. The universe does not guide that choice. It does not prefer one path over another. It offers the same laws to everyone, the same slowing of time, the same stretching of space, the same silent expansion in every direction. What we do with that is ours alone. You exist in a universe that spans 93 billion light-years, a structure so vast that even light, the fastest thing we know, requires billions of years just to cross it. From this small world, orbiting an ordinary star, you look outward at distances that numbers struggle to contain, and yet, somewhere within that scale, there is a quiet possibility that a single human life, measured not by Earth's clocks but by its own experience, could reach farther than any journey in history, could cross regions of space that today exist only as faint points of light, could move through the universe not as a distant observer, but as a presence within it. The universe has not closed itself to us. It has simply asked a price. A price in energy, in time, in patience across generations, and perhaps most of all, a price in what we are willing to leave behind. Because every great journey carries a quiet truth. The farther you go, the more distant home becomes, somewhere between the speeds we have already reached and those we can only imagine. There is a threshold, a point where exploration is no longer a dream, but a choice. And when that moment comes, the question will not be how far we can go. It will be how far we are willing to go. So for now, we remain here, on this small planet, beneath a sky filled with light that has traveled for ages just to reach us. And perhaps that is enough for tonight, because even without leaving, you are already part of something vast, something still expanding, something still waiting, and somewhere out there, in the quiet dark between the stars, the universe continues,